the Monte Carlo method. And so probably a lot of what I'm going to talk about today, you're probably already familiar with or have heard about, so it might be review, but it kind of gives you a little bit of a context into how we in engineering use high-performance computing and advanced computing methods to actually solve problems, because ultimately that's the end goal. Computing is a tool for us, and so we want to solve problems with it. So I'll give a quick overview of myself, some background with kind of how PDEs fit into this framework, and then I'll give a little bit of context at the end with a different way of solving PDEs known as the Monte Carlo method and quantum locks. And then I'll talk a little bit about the project challenge if you want to do some background reading before the formal announcement is made in a couple of weeks. So a bit about me. I've kind of been all over the place for a long time now. Quantum computing, interestingly, I discovered back in 2000 with this issue of Scientific American, which was actually about teleportation. But it kind of had this silly comic in there that was called The Quantum Adventures of Alice and Bob, which I thought that was kind of funny at the time, but that was the first time I learned the word qubit. And so put that on the back burner for about 15 years and then finally stumbled back into quantum computing, at my job now. Played around with nuclear fusion as a hobby in my basement, kind of like Bardon mentioned. You can actually find plans for these things on the internet. There's a whole hobby built around this Farnsworth fuser thing. And then kind of dovetailed from that into my university career at Rensselaer Polytechnic Institute, where I studied nuclear engineering. So did my undergrad there and then did my PhD there in neutron physics measurements. Also got a license to operate the research reactor, which you can see me standing in that picture there. And interestingly, if you're interested in quantum computing, RPI now has a quantum computer on campus, the only one of its kind of that size. So if that's something you're thinking about for either undergraduate or graduate school, something to consider. Nowadays, I work at the Naval Nuclear Laboratory here in upstate New York. I mainly work on scientific computing and emerging technologies, and kind of the things that need to go from 0 to 1, right? So you have some, newly discovered thing and you want to build, sort of a prototype or a product out of it. So kind of bridging that gap from getting it out of the lab and into the hands of the people who would then be the end users. So I got into quantum computing around 2017, originally motivated by the deuterium paper from Oak Ridge National Lab, where they actually solved the ground state energy of a nucleus using the variational quantum eigensolver algorithm. So that was, coming from a nuclear background, to me, that was kind of the signal that, hey, there might be something worth looking at here. And so one thing led to another, and here we are. So a little bit more about our lab. So the Naval Nuclear Laboratory goes back more than 75 years. It kind of started with Admiral Rickover's commissioning of this nuclear propulsion branch. And basically, the lab's mission is to build the nuclear power plants that go on Navy ships. And so we're under the Department of Energy. We have the Navy as our customer, and it's really a full stack nuclear engineering organization. So research, design, testing, maintenance, disposal, full life cycle of all of the nuclear reactors. And so some of the program firsts that we sort of have to our name are USS Nautilus, which is the first nuclear powered submarine, USS Enterprise, which is the first nuclear-powered aircraft carrier, as well as some tech transfer where we had the Shippingport reactor, which was the first commercial grid-scale reactor in the U.S., as well as Shippingport 3, which was the first thorium nuclear reactor. So lots of things that kind of this long history of innovation that we have here. And so when you think about what it takes to build a nuclear reactor, there's a lot of computational work that goes into doing that. So nuclear engineering is one of the heaviest users of high-performance computing. You have to solve lots of different equations. Lots of them are coupled. So you have to solve for how do the neutrons move through the reactor and through shielding. How do the fluids move? So you have to get the heat out of this thing that is fissioning and generating lots of heat. So there's thermal hydraulics and fluid dynamics. You have lots of materials of many different kinds under very harsh conditions. So there's lots of material science work that has to be done. And then in an integrated sense, you have to figure out, well, how reliable is this thing? It has to last decades in operation. So there's simulations that are done for the reliability analysis. And then you tie it all together with coupling all these PDEs and doing a multi-physics calculation. So from the standpoint of what does this look like in practice, it typically takes multiple petascale class supercomputers to do these types of computations. Since some of these codes go back decades, most of them are CPU dominant workflows. And now as codes are being retired or updated, GPUs are coming online. as well as acceleration methods that use AI ML methods as surrogate models, like Abhishek was talking about in his talk. So how does quantum fit into all of this? So part of my job is looking at these future technologies and figuring out how they integrate with our existing engineering and computational workflows. So quantum being an emerging platform with potentially significant computational advantages, we want to look at that in addition to some of these other benefits that come from quantum technologies in general. So we follow kind of this multi-pronged strategy. So rather than trying to do everything ourselves, we work with collaborators. So Womanium and WISER is one of our collaborators for doing some of the research and development work that we have, but we also collaborate with many different universities and labs and nonprofit organizations to develop technologies in the computing and sensing and material space to find applications in our program. And so some highlights from our work with the Quantum Solutions Launchpad, which we're in our second year right now, and I've listed kind of all of our alumni from this program that have helped us out. And so we've mainly been looking at 3 different areas. So quantum algorithm benchmarking, so find some quantum algorithms that have some relevance to the types of engineering problems that we're interested in, and have a team go off and develop a solution, test it on some hardware, and give us a sense of where the technology is at right now. Quantum system architecture. So these are things like devices, quantum networks, and distributed quantum computing. Design that system, kind of give us a sense of what it looks like, so that way we can, sort of figure out where does the future go, what are the big drivers of things like cost and complexity, things like that. And then finally, some work on the theory, methods, and simulations, both quantum and classical. So quantum simulations, but also classical simulations of quantum systems. And so we have, you can see, a very large group of people that have helped us out with this. And last year we had the opportunity to get everybody together and do some lab tours and conference presentations. So ultimately, the question we want to answer is, why do we want to do this modeling and simulation in the first place? So we have to solve PDEs. We have to spend a lot of money and electricity running these things on computers. So why do we want to do it? And the answer is pretty simple. We need to do hard, complicated things. So we have to design and operate big systems, like whether it's a spacecraft or a nuclear reactor. We want to understand how nature works. So we want to do weather forecasting and predict different scenarios. And ultimately, the experiments needed to do these things are not feasible, right? If we want to, see how is a car going to perform in an accident, it's kind of dangerous and expensive to keep crashing cars over and over again. Sometimes it's too expensive to do the experiment. We only get one shot at doing it. And sometimes it's just too big and complicated to even try, right? If we want to model how galaxies move through the universe, we can't exactly reconfigure many different sets of galaxies and try that. So that's why we do these simulations, because we can understand the physics well enough and then make some statements about, if we scale it to a certain system, how is that system going to perform? And today we've gotten to the point where computers are very powerful. We're in the exascale regime, so 10 to the 18th floating point operations per second. And our software tools and programming languages have made us highly productive. You can make the argument even now with LLMs, we can be even more productive, although it's hit or miss sometimes depending on what exactly code you're trying to write. So in practice, when we try and solve these problems, we start with the question. So what do we want to know about the system? And then we have to model the problem. So that's where the PDE part comes in. What governing equation describes how this system behaves? Then we have to map that model to hardware. So classically, that typically means coming up with some matrix equation and then getting that to work on CPUs and GPUs. And then we have to solve the problem. And then very importantly, we have to check our answer. So we can't just run the code and get an answer and say we're done. We have to run many permutations of it with many different sensitivities to actually see what's the error bar on that. How good is my answer? And then finally, we have to report our findings. So if we're going to be building something from this, we have to go to the engineers and say, these are the results of our calculations. This is how certain we are. Make a decision on whether or not this system is safe to qualify for operation. And so, like we've been hearing, the modeling part of this comes down to partial differential equations. So pretty much every physical phenomenon you can think of is modeled using a PDE. These do not generally have analytical solutions, except in very rare cases. So you can't just use algebra and calculus party tricks to get a solution. You have to do some numerical computation. So it's very limited exceptions where you can do that. And so numerical methods are that approximate solution that you use. So Navier-Stokes, like we heard about for flows, Schrodinger's equation if we're talking about quantum systems, And then the heat equation, if we're looking at like just how does heat flow through this metal bar here in the picture. And so the real world is continuous at the scales that we care about, but on a computer, we only have discrete elements. We have bits. So the first step we have to do is we have to discretize the problem. So we chop it up into these little mesh cells, and then we have to come up with some mathematical representation that, in the limit of making those mesh cells really tiny, we recover the original answer. And then, we have to prove that it converges to that answer. We have to prove that it's stable. So those are the two main things that you do when coming up with a numerical method to approximate a PDE. So you prove convergence and you prove stability. So that's numerical analysis. But once you have a discretized problem, then you can use linear algebra to solve it. And so there's different PDE discretizations that you may have heard about already. But once you've chopped something up into these different mesh cells, you then implement something like a finite difference. So you actually use the mesh cell and come up with a derivative that is approximated by that finite cell size. You can do finite volume, which is common in fluid dynamics, where you're just doing a material balance through the faces of a box of a cell. And then finally, there's the finite element method, which is a little more numerically complicated, but basically you're coming up with what's called the weak form of a solution, and then you expand that solution in some basis functions, and then you find the set of coefficients using a optimization method to come up with the final solution. All of that, though, is basically expressed as a matrix equation. So it's a system of equations and a system of unknowns. You write that as a matrix, and then you invert the matrix. So either you do it directly to get the solution vector, or you do an iterative solution process where you converge towards the solution. So one PDE that is of particular interest to many different areas is the Boltzmann transport equation. And so the Navier-Stokes equations actually can drop out of this equation in one form or another, but it also applies to flows where the fluid is not tightly coupled with itself. So for things like radiation and particle flow and rarefied gases, the Boltzmann transport equation is what's typically used. And so this is basically a balance equation. So you're looking at the change over time in some particles moving through a particular region of space is equal to sources minus how many are streaming, how many are just flying away, minus how many are colliding with each other and changing their direction or changing their energy or being absorbed and what have you. So this equation was actually one of the first applications of computing at all back in the days of the Manhattan Project, using for nuclear energy and astrophysics. But it gets applied to lots of different things like solar irradiance, when you're trying to figure out like what's the heat balance in the atmosphere, heat transfer for things like an oven, astrophysics for stars and supernovae. It actually is used in graphics rendering. So if you're trying to figure out how light is shining on a scene of objects, this equation, some form of this equation is being solved. Nuclear power for both how do neutrons move through the reactor, but also how do they move through shielding. And then finally, rarefied gases. So kind of like in the upper atmosphere when you have spacecraft flowing through that. And so a little more complicated version of that now is here in this equation form. You're basically trying to solve this distribution of particles in a 7-dimensional state space. So 7 dimensions, so you have space, x, y, z, direction, you have theta and phi. You have energy or velocity, and then you have time. And so those are your 7 dimensions, and then you have to solve for all that stuff, which makes it very complicated. And then there's a linear form of this equation that's typically solved that assumes that the particles are all the same type and they don't interact with each other. And so that's kind of the playing field for solving the Boltzmann transport equation. So now you have to discretize it. So what does that mean? So the first thing is ignore the dimensions that you can. So it means, what if we can do it time independent, steady state? So nothing's changing with time. Everything's monoenergetic. So like I did this experiment here in a glass of water with a laser, actually. So this is a transport problem. You have photons flying through some water, and they can either scatter, they can be absorbed, or they can just stream through the other side of the glass. And so you can make approximations based off of what is the medium that the particles are moving through. If it's clear water, you have to explicitly treat all the different angles that the light could go in. But if you put a drop of milk in that water, now it becomes cloudy and the photons are bouncing around and scattering a lot. So you can say, well, now this is a diffusive problem. So you can remove some of the angular dependence. So if you have a highly diffusive problem, that's another variable you can get rid of. And so there's lots of different ways you can handle all those things. But the true gold standard that gets used a lot in all kinds of different Boltzmann transport problems is the Monte Carlo method. Because fundamentally, radiation transport is a discrete process. You have individual particles moving around in a system and undergoing discrete interactions. So some of these are classical interactions and some of these are quantum interactions, depending on the type of particle, depending on the length scales, and depending on what they're interacting with. But the bottom line is individual particles interact with the surrounding environment in discrete events. And these interactions are probabilistic, typically governed by quantum mechanics. And so instead of discretizing the equation set, we can instead just directly simulate the particle interactions and then tally up what's actually going on in the system. So instead of treating it like a PDE, we treat it like a statistical sampling process. And so now it becomes analogous to a real experiment or an observation that we would make. And so this can handle arbitrarily complex physical processes and geometries, right? So you can simulate rolling a dice, you can simulate drawing from a deck of cards, or you can simulate a shower of cosmic rays on a detector, like in the picture here. You're really only limited by how accurately can you model the geometry and how accurate is the interaction probability data that you take into your system. And so the downside on a classical computer is that you sometimes have long run times and slow convergence, particularly if you're trying to model rare events. So if you're just naively throwing particles into a system and trying to figure out, well, like, what's the probability that they make it to this particular spot right here, it may take a very long time to get to that point. And so the solution converges generally as 1 over the square root of n, where n is the number of trials that result in a tally in your particular quantity of interest. And so you can get some improvement with statistical tricks. But what's interesting about quantum computing is that you can get at least a quadratic improvement if you format it as a Grover search problem. And so there are other quantum Monte Carlo algorithms that get even better scaling performance. And so the interest right now is trying to figure out where is the advantage, like what characterizes that type of advantage, and how do you then apply that to an engineering type problem. So here's a simple example of a Monte Carlo problem. It's a random walk on a line. So you can either model it like this, where you have a ball. At each time step, you have a probability of 50% to go to the right or to go to the left. Or you can model it like the Plinko board game here, where you just drop marbles down this board, and then they hit a peg, and then they just kind of diffuse through all these different pegs, and then they land in a bin at the bottom. And in the limit of an infinite number of marbles, you get a normal distribution. So this is a type of random walk problem, and this is the kind of thing you can solve with a Monte Carlo method. So the question then is, what does this look like on a quantum computer? So you can do this with quantum states. So you can either model the conditional probability of this marble bouncing down the different pegs as it goes through the system, or you can remove that conditional aspect of it and let the quantum states interfere with each other as they move through the system. And you wind up with a different distribution at the end, which actually tallies either quadratically or up to exponentially faster than it would in a classical system. And so if you have a probabilistic PDE, you can model this with a quantum walk. And that's what the project is about, is understanding how to develop this kind of model and then how to optimize it to run on contemporary hardware. And so a very simple version of a quantum walk on this Plinko board model is to model it this way, right? So let's look at just a single peg. We start with 1 qubit set to the 1 state. So that's qubit 2 in this picture here. And then qubits 1 and 3 represent the blue bin and the yellow bin. And then qubit 0 is our control qubit. So we can use this combination of Hadamard, controlled knot, and controlled swap operations to then mark all the execution paths that this ball can take as it moves through the system. And then when it finally gets to the end, we then do the measurement of the tally bins to get a distribution of the final position. So the project then is based off of this model. So there's a paper by Mark from the Quantum Village at DEF CON, actually, called the Universal Statistical Simulator. So if you follow this link here to the archive paper on this, there's a quantum circuit that you can then paste into Qiskit or what have you to then implement this for a 1 and 2 time step case. So the challenge will be, re-implement this problem, and then generalize it for any number of time steps through this Monte Carlo problem. And then the question is, how do you change the gates so that way you get different distributions? So if you just use Hadamard gates, it's just a 50-50 distribution. And then finally, instead of using an idealized problem, if you use a noise model, what's the biggest problem you can run and still get an accurate distribution compared to the classical example? So more details on that will come out in a couple of weeks, but if you want to start thinking about it, this is what the project challenge is going to look like. So that's all I got. So thanks for listening, and I'm happy to take a few questions with the time we have left.